In the previous lectures, you've learned how the flow conditions and the sediment grain size influence the formation of specific bed forms like ripples or dunes that form in unidirectional flow. So these slides will focus on the sedimentary structures that are produced by the migration of those bed forms. The structures are the things you can actually observe in the sedimentary rock record, and what we're going to be using in class later on and on field trips to distinguish between the different depositional environments. So the general strategy is that we'll use the characteristics of the sedimentary deposits, like their grain size, sedimentary structures, and so forth, to infer the type of fluvial setting that might have generated them by making comparisons to modern rivers. So this approach builds these idealized models called facies models that outline all the sedimentary characteristics of a particular environment. The next lecture will cover what a facies is and what facies models are in more detail, but briefly, a facies is just a recognizable unit of rock that is defined by all of its characteristics, the rock type, the grain size, sedimentary structures, textures, and really any other observation that you could potentially make. So you learned last class how the bed forms that develop under unidirectional water flow are influenced by sediment grain size and current velocity, including this very important diagram here. Under typical river conditions, ripples and dunes are pretty much the main bed forms that you would expect to find. There are rare braided river systems that are dominated by upper plain bed stratification, but that requires fairly unusual conditions. The river has to be supplied really only with a very restricted range of very fine sediment, which is not very typical. So because ripples and dunes are the predominant bed forms in really any type of river, we'll focus on their sedimentary structures in this video. So you may remember that both ripples and dunes migrate in a similar fashion. They erode on the upstream or stoss side, and deposition occurs on the steeper downstream lee side. This pattern of sediment transport arises because of the water flow and the velocity changes as the water interacts with the bed, but it occurs in the laminar sublayer for ripples and in the turbulent boundary layer for dunes. So basically, in this sediment transport, the sediment grains slide or roll or bounce or otherwise move up the gentle stoss slope until they reach the top of the crest, labeled the brink point in this diagram here. Sediment will build up at that point there until the crest gets too steep, and that oversteepened lee face collapses and the grains avalanche down into the trough. Those grain avalanches end up producing steeply inclined layering called cross-stratification, or cross-strata on this diagram here. You'll sometimes hear it referred to as cross-lamination or cross-bedding. One important point to note is that the cross-stratification is produced at this dark blue line on the diagram on the lee face, but you can see from the diagram again how it actually immediately starts to be eroded as the crest and the upstream part of the bed form, like the ripple, migrates over that point. In this example here, nothing actually remains of the cross-stratification by the time the ripple has completely passed over that point. So for the cross-stratification to be preserved as a sedimentary structure in the rock record, there actually has to be more sediment accumulating in the area than there is erosion. And this allows the bed form to migrate slightly upwards as it's moving downstream. So in that case, if the bed form moves slightly upwards, the erosion from the trailing part of the stoss side will chop off the top part of it, but it won't erase the entire height of the bed form. So if there is enough sediment supply, and if deposition exceeds erosion, the bed form will aggrade or move upwards, and at least part of the cross-stratification will be preserved. Generally, just the lower part gets preserved as the top part of the bed form gets sawed off by erosion as the bed forms pass over that point. For a ripple or for a dune with a straight crest, so for example, if you look down on the bed form from above, the crest would look straight. The type of cross-stratification that it forms is called planar cross-stratification. It's basically a giant dipping plane, which in this case, in this photo, we're viewing from the side. These straight-crested bed forms are sometimes called two-dimensional or 2D bed forms as well. This particular example illustrated here are from dunes. Remember that ripples are only a couple centimeters tall, and so this cross-stratification here is much too large to have been generated by ripples. Cross-stratification also has another widespread use, and that's to indicate the direction of current flow. The inclined layers in these crossbeds are also called foresets, and they, as you've seen in the previous slides, are the downstream or lee side of the bed form. So therefore, these foresets dip in the current direction. In this photo, they're dipping to the left, and so the current flowed from right to left, approximately right to left. It's actually important to be able to view the cross-stratification in 3 dimensions to accurately determine the dip direction of the plane. This cross-stratification was also from a dune. The small red bar there is actually a 10-centimeter scale bar, so this is a very large dune. But I'll confess that this is not from a river. It's actually dunes from a shallow marine environment. As I mentioned earlier, the vast majority of crossbedding preserves only the bottom part, or the toe, of these inclined foreset beds, because the top of the bed form gets eroded away. However, in areas where the sedimentation rate is really, really high, the ripples, or the dunes, in this case it's primarily ripples, can aggrade or build upwards quickly enough that they don't even erode the previous layers at all. In that way, they climb up the backs of the previously deposited ripples, and therefore, quite descriptively, are called climbing ripples. These climbing ripples end up not being very common in rivers, but they are more likely to form in water where the water velocity decreases somewhat abruptly or somewhat rapidly. In that case, the very rapid deceleration of the flow allows some of the sediment that was carried in the suspended load to drop out of suspension, which leads to these really high sedimentation rates. That condition of very rapidly decelerating flow is more common in delta environments, and so we'll come back to climbing ripples when we talk about deltas, but it can occur in some fluvial settings as well. So here's a picture that includes some climbing ripples, the thick layer of ripple cross-stratification in the middle of the bed there. In this case, you can see how the entire ripple crest is preserved, and the cross-stratification is climbing to the right and also diagonally upwards. You can see the gentle stoss side and the steeper lee side of each of the ripples. Again, the lee side is facing to the right in this case, which indicates a flow approximately from left to right. But again, remember to look in 3 dimensions when you're actually out on the outcrop. If the bed form crests are not straight, so they can be sinuous or can have a variety of more complicated shapes like these linguoid or cuspate or lunate bed forms, the bed forms are called 3-dimensional or 3D. As a general rule of thumb, 3D bed forms are thought to be higher energy features than 2D bed forms. Migration of 3D bed forms produces something called trough cross-stratification. There still are angled or inclined foreset beds, shown on the right-hand photo here, but they aren't part of planar surfaces like in the planar cross-stratification. Instead, they are separated by these scooped-out troughs that have various shapes depending on the shape of the bed form. The left photo shows the end-on view of these troughs. You can also refer to the title slide of this lecture video to see another block diagram of 3-dimensional view of trough cross-stratification. The foresets of the trough cross-stratification also dip in the downstream direction, indicating in this case a flow generally from left to right. But because of their irregular shape, it's really even more important to be able to view these in 3 dimensions if you're trying to analyze the paleocurrent. So I want to end with a brief mention of one final sedimentary structure, one that you're likely to find in deposits from gravel-rich or coarser-grained rivers. So if you refer back to the bed form diagram, you'll see that you can get dune bed forms even in pebbly or fairly coarse-grained sediments. That's true, and the migration of these bar bed forms that you see in the photo here can also produce fairly large-scale foreset beds. But in general, in these sort of rivers, the stratification or layering is pretty poorly developed. Because of the wide range of grain sizes and the wide range of grain shapes and the generally coarse size of all the particles, the beds end up being pretty crudely organized, and may look massive. In this case, massive refers to a lack of distinct layering and not to any sort of large size or anything like that. So in this case, the bedding might not be very obvious, but what you do sometimes find is that the pebbles or whatever grains you have in the sediment often develop this preferred orientation called imbrication. And so the presence of imbricated clasts in a conglomerate, a clast is just the larger rock particle contained within the conglomerate itself. So the presence of imbricated clasts can be highly characteristic of traction movement, like rolling or sliding of larger particles, like you would find in river flow. So when one of these irregularly shaped particles is moved in the bed load, it tends to move following the path of least resistance. In the case of elongated particles, that makes it easiest for them to roll around their long axis rather than trying to flip over completely around in any of the other directions. The rocks also can tend to get stuck on each other or on other rocks in the sediment and line up like these sort of stacks of poker chips you could think of. That sort of fabric with these stacked rocks all lined up with their flat sides pointing upstream is what's called this imbricated fabric. In the picture, you can kind of get the impression of a general alignment of the rocks. They're going to be pointing up and to the left, and they have their larger, flatter sides pointing up and to the right. This would indicate a current flowing generally from right to left in this photo. You can also see some areas in the photo where there are a few rocks stacked up against each other. You might find 3 or 4 or 5 of them all with kind of the same sort of orientation. Although you'll notice that the organization here isn't that uniform. It's pretty disorganized due to the mixtures of sizes and shapes of the particles. So keeping this sedimentary structure in mind here when we talk about alluvial fan deposits in a week or so, and especially when we go on our first field trip.